A little bit of practice now with both graphing some of our polar functions in our calculator, but also working with their derivatives a bit more. So let's take a look at this first problem. Graph 2 minus 2 cosine theta, this polar function, and then find where it has horizontal and vertical tangent lines. And we're going to do this by hand. We're going to do all of our graphing using our calculator, obviously, but we're going to find the tangents by hand. Now, just make sure we understand what we're going to attempt to do before we start working through it. Since we're looking for horizontal and vertical tangents, right, we're looking to see where some information regarding dy dx. Okay, so that means we're going to need to come up with the equations for x and for y. So first things first, go ahead and graph this into your graphing calculator. I went ahead and sketched it out for you. It's not actually a great uh, it's not actually in the right spot, first off. It should actually be something like that. Sorry about that. It should actually look something like this, and go ahead and graph it out just to make sure you know what you're referencing, because we're actually going to need to do some work with it. So first things first, let's go ahead and find our equation for x. So we know x is equal to r cosine theta, so we're going to go ahead and write this 2 minus 2 cosine theta, all of that times cosine theta. I'm going to put that in parentheses so we can make sure we distribute. So x is equal to 2 cosine theta minus 2 cosine squared theta. Now, since we need to find horizontal and vertical tangent lines, again, we're going to need to also know what dx d theta is. So let's differentiate this. So this is going to give me negative 2 sine theta. And then over here, we're going to say 4 times cosine theta times sine theta. So let's just go ahead and do that. Times cosine theta times sine theta. All right. Next up, now let's go ahead and find our equation for y, and I'll do that in different color. So y is equal to 2 minus 2 cosine theta, all of that times sine theta. So y is equal to 2 sine theta minus 2, and if I multiply sine theta, cosine theta, we could have 2 sine theta cosine theta. Okay, and now let's find the derivative for dy d theta. So if we do that, and actually I might have wanted to rewrite this here using the double angle identity, just might make it so that we don't have to use the product rule when we are differentiating. So I'm going to rewrite that, all of that, as the sine of 2 theta. All of this is, let me write that first. All of that is equal to the sine of 2 theta before I erase it. So we're going to just basically subtract minus sine 2 theta. So now when we differentiate this, we've got 2 cosine theta minus, let's say to get the derivative of the inside, that's 2, and then we're going to say cosine of 2 theta. So we have that. Okay. Now that we have our x and y equations and we have their derivatives, dx d theta, dy d theta, now let's make sure we understand what we're looking for here. It's asking us to find where we have horizontal and vertical tangent lines. Now remember, if we're looking at a horizontal tangent line, what do we know then about its slope? We know that if it is a horizontal tangent line, that our m value is equal to 0. In other words, dy dx must be equal to 0. And the only way that this could be equal to 0 is if your numerator is equal to 0. Okay, so that's where, actually, maybe I'll do this in red so we can kind of match that up. So if we're looking for a vertical tangent line, it's where dy d theta is equal to, dy dx, excuse me, is equal to 0. So a vertical tangent line. Okay, that means dy dx has to be equal to 0. Now let's switch to talking about the horizontal tangent. Oh, I realized I wrote the wrong thing. Sorry. Before I confuse anyone any further. So if we're saying the dy dx is equal to 0, I apologize. That should mean that we have a horizontal tangent line. So all this, I'm going to switch back over to the right spot. Apologize, it's a Friday afternoon, but I'm recording this for y'all. All right, so we got a horizontal tangent line. All right, here we go. So horizontal tangent line is when the numerator is equal to 0. Okay, I think I'm square now. All right, now we have the vertical tangent line, okay? So if we're looking at a vertical tangent line, that means if our tangent line is vertical like this, the only way that that can be vertical is if you have 0 in your denominator, right? So if that is in the denominator, since dy dx is equal to dy d theta all over dx d theta, the only way that this could be a vertical tangent line is if dx d theta is equal to 0. So all this to say, we're going to look for where dx d theta is equal to 0. Okay, so I'm going to write that, where dx d theta is equal to 0. And let me erase the vertical tangent line. You all know what that looks like by now. So when our dx d theta is equal to 0, then we have a vertical tangent line. When dy dx is equal to 0, which also is another way of just saying when dy d theta, in other words, our numerator is equal to 0, then we have a horizontal tangent line. All right, so now let's actually find them. So first off, where is let's start with finding our vertical tangent line. Let's do that. So for our vertical tangent line, and for as much as I've fixed all this, I realize my colors are still messed up. So this is technically correct. Vertical tangent line is where dx d theta is equal to 0, but that should be blue since we care about consistency's sake. And then this here should be red. All right. I think I'm finally in the right spots here. Okay, so now we're ready to do all this. Okay, here we go. So starting with this, we are then going to say the following. So if I want to go ahead and do the vertical tangent line here, I'm going to set my dx d theta equal to 0. So one thing that I could just do here to make my life a bit easier is set 0 equal to negative 2 sine theta minus 4 sine theta cosine theta. And then looking at this here, it probably would be easiest if I just went ahead and I factored out a 2 sine theta. Sorry, I should say this should be positive, if I'm not mistaken here. Yes, I believe that this up here should be positive. I made a mistake there. There we go. So if I factor out 2 sine theta, what are we left with? 2 sine theta, if I factor that out, I'm left with 1, or negative 1, I should say, plus 2 cosine theta. So now that we have that, let's go ahead and set each one of our factors equal to 0. So sine theta is equal to 0. And what do we have here? This is cosine theta is equal to positive 1/2. So theta is then equal to what values of theta make sine equal to 0? Well, there are two options. Then we got 0 and we have pi. Let's just look at all the angles between 0 and 2 pi non-inclusive. For cosine of theta to get equal to 1/2, what does theta have to be? Well, theta would have to be equal to pi over 3 and 5 pi over 3. Now keep in mind here, these aren't the actual coordinates just yet. These are just where our angles are. That's what are the angles, but these aren't the actual points yet. We'll find those in just a bit. But now let's move on to doing the horizontal tangent line values. So for the horizontal tangent line, and I'm now back to the right colors now, I'm pretty sure. So we're looking to see where is dy d theta equal to 0. So we're going to set our dy d theta that we found up there, 2 cosine theta minus 2 cosine 2 theta, and we're setting that equal to 0. We're setting our derivative of dy d theta equal to 0. And since we have a 2 in front of both of these, we can just go ahead and divide those out. We won't need those. And we can't just factor here because we have a cosine theta and a cosine of 2 theta. So we may want to use a trig identity here, or the double angle formula. And if you remember the double angle formula for cosine, there are 2 available, or excuse me, 3 available to us. And I'm going to try to write all my terms in terms of cosine, of the function cosine. So I'm going to say cosine of theta minus, and I'm going to rewrite this as 2 cosine squared theta minus 1. And if I distribute that, let's see here. That's cosine theta. Well, actually, let's write this in the correct order. We've got negative 2 cosine squared theta plus cosine theta plus 1. And I know this is kind of silly, but I like having my leading coefficient being positive. So I'm going to go through and just divide everything by negative 1. Now let's factor. So we got 2 cosine theta, 1 cosine theta, This has to be 1. Well, this would have to be negative, and this is positive. So now we can say cosine of theta is equal to negative 1/2 and 1. So where are the angles where that occurs? Cosine of theta is going to be equal to negative 1/2 when theta is equal to 2 pi over 3 and 4 pi over 3. And then cosine of theta is equal to positive 1 when theta is equal to 0. All right, so despite a little bit of a bumpy road with me mixing up, writing down where I'm finding the horizontal and vertical tangent lines, I think the rest of this is all correct. So let me make this a little bit smaller so I have some space to work with here. But now that we have that, now let's actually think about this conceptually for a second. So first off, we're saying that we have vertical tangent lines when theta is equal to 0, pi, pi over 3, and 5 pi over 3. However, let me draw to your attention the fact that I am getting a value of 0 in both my vertical and my tangent line, horizontal tangent line places. Well, what's happening when theta is equal to 0? When theta is equal to 0, notice that point there. So for that cardioid, what we have here is a cusp. And think back to what we know about the differentiability at cusps. We see that it's a non-differentiable point here because we see that the one-sided limits are going to be both approaching negative infinity. So because the limit doesn't exist, we would say that this cusp here it's a non-differentiable point because we cannot find the derivative there at that point. Now, for that reason, and the fact that we're seeing here that theta is equal to 0 for both so when theta is equal to 0, dx d theta is equal to 0, dy d theta is equal to 0. So what is happening with dy dx? We have a 0 over 0 situation. So that's more of an identifier and signifier to us that this point is not going to be differentiable, right? We have a cusp. There, in other words, a tangent line cannot exist there. So we would not include it in our list of places where there is a horizontal or vertical tangent line if there is no tangent line at all. So what that means is we are going to disregard that from our list. We don't need to think about those. Instead, let's just go into finding our points for pi, pi over 3, and 5 pi over 3. So when theta is equal to pi, we're going to plug it back into our original polar function. And what is our r value? Well, cosine of pi is equal to negative 1. 2 minus 2 times negative 1 is just 4. So our coordinate is 4 pi. When theta is equal to pi over 3, I get positive 1. I do get positive 1/2. So then that would give me 1 comma pi over 3. 5 pi over 3 gives me the same cosine value, so that's going to be 1 comma 5 pi over 3. So let's think about this for a second. These are the points where we are seeing a vertical tangent line. So at 4 pi, and I'm realizing even more now that my graph was actually sloppier than I wanted it to be. This should actually look something like this, and this should look like this. All right, so that's a better looking cardioid. Those of you who probably noticed that I messed up from the get-go are finally feeling that anxiety wear off. All right, so at 4 pi, I've got a vertical tangent line. At 1 pi over 3, which is right around here, I've got a vertical tangent line. And 1/5 pi over 3, which is right around there, I've also got a vertical tangent line. Now let's establish our horizontal tangent lines. When theta is equal to 2 pi over 3, what does r give me? So let's plug in 2 pi over 3 in for that r function, our polar function. When theta is equal to 2 pi over 3, I believe I get 3. So 2 pi over 3. And we also have 4 pi over 3. So if we disregard theta is equal to 0, this is where we're seeing horizontal tangent lines. So that's, again, this is just a rough sketch, but right around there, we've got a horizontal tangent line, and right here at 4 pi over 3. So it was a lengthier problem, but hopefully now we get a better sense of how that works. So we can now find both horizontal and vertical tangents by hand. I'm going to go ahead and make this a bit smaller. Again, if you have access to my Google Classroom, you can see my worked out solutions to this. I'm just going to leave that up here because now I want to move on to this next problem. So for this problem here, we're going to go ahead and we're going to graph this function, and then we're going to find the greatest distance from any point on the curve to the pole. So first, pause the video and go ahead and graph that function for yourself, because this one we are indeed going to be using our calculator a bit more. The last one, we didn't really need to use our calculator other than graphing the original function. So if you graph that out, here's what it looks like. And notice that also that our interval is from 0 to 3 pi over 2, or 1.5 pi. Okay. If you didn't do that, then your graph is going to look a little bit larger than this, but this was the only part of the polar function I was interested in. Now, part A, this is where we want to have a bulk of our conversation. It asks us to find the greatest distance from any point on the curve to the pole. Think about what this is saying. We're basically asking ourselves, where do we think we have the largest value of r? What is the largest distance from our pole to some point on the curve? Well, instead of us guessing, how can we use calculus to figure that out? Effectively, what we're asking for is the maximum value, and I'll write that. We're looking for the maximum value for r. Now, what have we done in calculus in the past to find the maximum values of functions? Well, the hint, and this is where I've worded it a little bit poorly, it's not so much about us finding the absolute maximum of the derivative, but we are going to indeed use the derivative. So I should rewrite it as that. We're gonna think of the derivative. If you think all the way back to us working with polynomial functions, for example, how did we find maxes and mins on our graph? Well, we used the first derivative. We found the places where our derivative was equal to 0, and we saw a sign change, right? Think back to the first derivative test. That's exactly what we're going to be doing here, but we're just working with polar functions. So what we're going to be looking for is where dr d theta is equal to 0 and a sign change. That's where we are going to see a possible maximum or a minimum. Now, before I actually try this, let's make sure we understand what dr d theta is saying. Dr d theta is effectively describing how much the distance from the origin is changing at a point given a small change in theta. I'll say that one more time. Dr d theta is describing how much the distance from the origin is changing at a point given a small change or a little change in theta. So if our dr d theta then is positive, what does that mean? Pause the video and think about that. If dr d theta is positive, what we're saying is that our r value is getting larger. In other words, we are moving away from the pole. Because when our r value is equal to 0, then we're starting to see that then our point would be at the pole. As r then starts to increase with some change in theta, then our r value, we're increasing our distance away from the pole. When dr d theta is less than 0, then our r is getting closer to the pole, right? It's getting smaller. It's moving towards the pole. So this is a game changer for us in the way that we think about this. With rectangular functions, when we looked at derivatives, the fact that our derivative was positive and negative told us information about the slopes of our tangent lines. In other words, when our functions were increasing and decreasing. With polar functions, what we're effectively looking at is, does it look like our r value is moving away from the pole, or does it look like it's moving towards the pole? So for example, this region right over here, or this part of the curve, we can see that our r values are moving towards the pole. So we would say that dr d theta then would be less than 0 there. It looks like our dr d theta is negative there. All right, so now that we have an understanding of what's going on with dr d theta and what it means, now let's actually find our derivative of r and use it to find the maximum value of r. So part A, what is dr d theta? Dr d theta, let's just find the derivative here. We're just going to use the product rule. That would be 1.5 cosine of theta plus 1.5 theta times negative sine theta. Now we're ready to set this equal to 0. So we're going to set all of this that we just found equal to 0. Okay. And this part we won't need to do by hand. We'll we'll be able to use our calculator. In fact, I want us to practice using our calculator here. So how do we do that? So in our calculator, we're going to change our function now. So take a moment, change your function, or change your calculator to function mode. Change to function mode. And you're going to graph this equation. You're going to graph drd theta, and you're going to graph it as a rectangular equation. And you're going to do that so that you can find the zeros. And so pause and go ahead and try that. So change your function to your calculator to function mode and graph this. And you'll know you're doing it in the right mode when it effectively is going to ask you to enter in x's instead of thetas. And make sure that you keep your window from 0 to 3 pi over 2. And what that's going to do is that's going to give you a graph that looks something like this. And so what we're interested in are the following. We're interested in where are these zeros? What are these zeros such that the graph, the derivative is equal to 0, and so that we have a sign change from positive to negative, negative back to positive. So go ahead and use your 0 feature in your calculator to find those points. And what you hopefully found was the following. You hopefully found that x is equal to, or instead of x, I know your calculator is calling it x, but I'm going to call it theta, so we know what it means. 0.860, 3.4256. These are the two places here where our derivative is equal to 0. Now again, these aren't our maximums. We then need to take these values here and plug it back into r, into our original polar function, so that we can find what those r values are. No pun intended. So punch those in, and you should get the following. R is equal to 0.8416. And when we evaluate R at 3.4256, what does that give us? It's going to give us a negative value, but that's fine. Since we're concerned with the largest distance, we're concerned with the distance. We don't care if it's positive or negative. So we can even say the absolute value here. And we see that the largest distance away from the pole occurs when theta is equal to 3.4256. So this is our maximum value here. And think about for a second what we just found. We're saying when theta is equal to 3.4256 radians, which would mean theta is somewhere right around here, because we know here is pi radians. So when theta is right around there, we're seeing that since it's a negative r value, we're going to reflect it over the pole right around here. That looks like it's our maximum value of r, the max value of r, right? So right at that point. So we have just found the exact angle place where r produces a maximum value using what we know about the derivative. And again, this process is very similar to what we did earlier with basic rectangular functions. Now let's do part B. And in fact, part B is a lot easier. So at this point, if we know what dy d theta is, and it tells us the slope of the tangent line is 2 over 2 minus pi, then what is dx d theta at this point? Well, let's think about this for a second. You know that dy dx is equal to dy d theta, all of this over dx d theta. Well, if we want to solve for dx d theta, that means we're going to just rewrite this as dx d theta is equal to what? We would say dy dx, all of this divided by dy d theta. Well, what is dy dx? That's, what do we have here? We can say dy dx, we're told is 2 minus pi. Okay. Oh, I think I switched these around. I apologize, class. So this is what I get for rushing it. So this should be dx d theta if I multiply both sides by dx d theta. And so dx d theta should actually be dy d theta, all of that divided by dy dx. Okay. So now that I have that, let's move that up. And so dx d theta, what is dy d theta? Well, we know that dy d theta, we're told, is 1/2. And then dy dx, we're told, is 2 over 2 minus pi. And when we simplify right over there, we should get 2 minus pi, all of that over 4. Okay, so I know that I said that was easier, but I made a basic algebraic mistake myself. It happens. We all make mistakes. All right, now I know this is a longer video, so props to you if you've made it all the way to the end, but let's go ahead and just finish up by looking at the point of intersection between a system of equations. So for this one here, how do we find the point of intersection of any function? Well, the easiest way is just to set those two functions equal to each other. So we're going to set those equal to each other. Now, take a moment right now and go ahead and graph these two functions in your graphing calculator to make sure you can kind of visualize those points of intersection first before we actually solve here. And for us, our cardioid is going to look something like this, which is the top function here. So that's going to look something like this. And our circle is going to look something like this right over here. This is just a very quick sketch here. So we can kind of see what we think our points of intersection are going to be. But now let's confirm by actually solving this algebraically. So here we'd say that 2 is equal to 2 cosine theta. Cosine theta is equal to 1. So theta would have to be at either 0 and 2 pi. Now, typically we usually just give our angles between 0 and 2 pi non-inclusive because otherwise we start getting repeats. So we're just going to go with 0 here. That's fine. So now that we know what theta is, remember that's not our solution, we want to actually plug that back into any one of these two equations. Either one works because we're saying this is an angle that's true for both, that satisfies both equations and gives us the same r. So r is equal to 4 times cosine of 0, which means r is equal to 1. So our coordinate is equal to, 4, because we're multiplying by 4. So our coordinate is 4, 0. So there's our point of intersection. And if I wanted to, I would just call that a video and just say, hey, there we go. We found that point of intersection. There it is. But there should be something that should stick out to you and kind of bother you here. And the question is probably, well, what about this point right over here? This certainly looks like it's a point of intersection. But how come that didn't come up when we solved this algebraically? So it means one of two things. It means either it is a point of intersection, but somehow we don't know how to find that, or it isn't a point of intersection. And if not, why isn't that the case? Because it certainly looks like it's intersecting here. So I encourage you to pause the video and think about this for a second. Is that or is that not an actual point of intersection? Now, the answer is it isn't. Well, why not? Well, let's think about this for a second and break it down. In order for that to be a point of intersection, again, it has to be an r theta, a point that works for both equations. Well, it looks like it's happening when r is equal to 0. So let's try the first equation. When r is equal to 0 for our first polar function, what is theta? Well, here we'd say that cosine of theta is equal to -1. So theta here is equal to pi. That's what gives me -1. Well, now let's look at the second equation. So actually, let me finish writing that up. So that coordinate would be 0, pi. Now let's look at the circle. When r is equal to 0 for the circle, what is theta? So we're going to set r equal to 0 and solve there. Well, theta then here is when when is cosine of theta equal to 0? Well, theta is equal to pi over 2 or 3 pi over 2. So we've got two different coordinates here. So we have 0 pi over 2 and 0, 3 pi over 2. Now, take a look at these sets of coordinates and ask yourself, Are these coordinates the same? They're not. They're clearly not. So what's happening here? And this is what's so interesting and also maddening about polar functions is that they don't behave like rectangular functions. Even though it looks like the graphs are intersecting at that point, what's happening is that those functions are hitting that origin, that pole, at different angle measures. For the cardioid, it hits the pole when theta is equal to pi. For the circle, it hits the pole when theta is equal to pi over 2 and 3 pi over 2. If we were to think about this in terms of time, they're hitting the train station at different times. They're just missing each other. So even though it looks like they're intersecting there, our points are not the same. So these are not points of intersection. The only one that we could get would be for 4, comma 0. So hopefully that clears that up. And I encourage you to try the next one now that you have a pretty good sense of how to actually determine points of intersections for the system of equations in polar form.